Welcome to a discussion about buildings. And the thing about buildings that I like is that we can all relate to buildings. We live in buildings, we go to school in buildings, we work in buildings. As it turns out, we spend over 90% of our time in buildings as sort of most Americans, not everybody. And so we really need to understand what's going on inside these buildings. Just a little bit about me is I have founded a couple engineering consulting firms. I do a lot of engineering design of buildings, and it's the engineering team on buildings that needs to think about energy and water, sustainability, and all these other things. And I've also founded the Stanford Building Decarbonization Learning Accelerator, where we're creating teaching material for professors around building decarbonization. So I think a lot about how to teach this subject and talk to a lot of different professors about it. I also founded an unsuccessful company that made a heated and cooled chair for offices. It was really cool, but didn't make it. And then on the right is just a picture of the ASHRAE Journal, where myself and two of the engineers that I work with wrote an article about building decarbonization a couple years ago, and this is when people were just starting to hear about it. It's something I've been working on for a long time, and so this idea of building decarbonization, I hope by the time I'm done you'll have a sense of what it is, but it is right now transforming how people think about buildings. It is a fundamental shift, and I've been working in this field now for my whole career, which is plus or minus 40 years. And I have not seen a shift in the building industry as significant as the one that we're going through right now. So take note of what's happening. I work with a lot of different types of projects. I don't work so much on designing homes. I work what we call in the non-residential sector. So I work with owner-built buildings, like tech companies. They build their own building, right? And then they pay for it, and they build it, and then they occupy it. And I also work a lot on the higher ed side. I work with a lot of universities, and they're similar. They build their own buildings. But I also work with developers who they build buildings for other people, and that's a very unique thing. They're making decisions for their future tenants. And a lot of times those things don't necessarily align. And I also do a lot of work in the life science area, which is big. I like to start by talking a little bit about my past and some of the things I've learned along the way. When I was in college, I did an internship at the California Energy Commission. And this is a time when there was a big surge in solar energy, and mostly solar thermal energy, and that's using solar panels to make hot water, either for your domestic hot water heating or space heating in a building, and there was a lot of interest in that, and this is in the early 1980s. And so what we had was a 800 number, a phone number that you could call to get information on solar energy. So remember, this is before the internet, and if you need up-to-date information, what do? Right? You could go to the library and look at an encyclopedia, but that's usually not up to date, and so you would call a 800 number. That's what you would do. And so we were sort of the internet of days old there. And one person called and said, "You know, I've got a question. I'm looking for a solar clothes dryer, right? I want to dry my clothes with solar." And as an engineer, young engineer, I was thinking about, well, you know, we should probably have some panels and a big duct and a big system, all these fans, and it'd be expensive and everything. And I said, let me put you on hold for a minute because I haven't heard of this yet. And I asked the people in my room who were also doing the 800 number, but they were a little bit more experienced. I said, "Have you guys heard about a solar clothes dryer?" And they all started laughing. And I was like, "What?" And so I, in a sense, got pranked by a solar phone call. And the right answer is not this, it's this. Ha ha ha. So it's like, yeah, I got back on the phone. Very funny. Thank you very much. And to me, that was a very important lesson that I've tried to remember as much as I can, and it's something that now that I'm mentoring young engineers, I repeat often. Not necessarily a story, because after they hear it once, they don't want to hear it again. It's enough, right? But I say, look, the simple solution is oftentimes the best solution. And as an engineer, we tend to go towards more complex solutions oftentimes. And so a lot of times on buildings, I look for the more simple solutions. So some of the things we'll talk about are simple. Some of them are a little bit more complex. But for instance, today we don't have the big solar thermal panels with pumps and fans. What do we have? We have solar photovoltaics. And why is that better? It's still relatively high tech, but there's no moving parts. There's no moving parts, so it's simple and vastly more reliable. So in buildings, I try to think about it in a similar way. So basically what I've done, spent my most of my career doing, is hacking building systems, trying to figure out ways to make building systems work significantly more efficiently, but keep it simple at the same time. So you'll see lots of examples of that today. Why do buildings matter? You might or might not know that buildings are responsible for 39% of global greenhouse gas emissions, not SUVs like a lot of people believe. So buildings are super significant. And in buildings, there's two elements that make up those emissions. One is the operating emissions, that is, when we use energy, there's usually, not always, but oftentimes a greenhouse gas emission related to that, right? So for burning gas in the building or using electricity that was made with a fossil fuel, there's CO2 emissions related to that. The other thing is building materials. When we make building materials, we use energy, or in making the building material, there's a reaction that releases CO2 or some other greenhouse gas. Like refrigerants for cooling systems, refrigerants do release or are greenhouse gases in and of themselves. So building materials are part of the picture as well. I also did want to make the point that building emissions or energy emissions, and I'm hoping that you guys have talked about this, they do have a negative impact on our health. Okay, and so we could talk about climate change as sort of a future thing, although we're starting to feel it now, but in air quality in America and many other countries is significantly poorer because of particulate emissions and emissions from burning fossil fuels. And there's an environmental justice part in that as well, that Black communities in our country have a disproportionate burden of these negative emissions. And so that is something that the faster we can get fossil fuels out of the picture, the better off we're all going to be, but also we'll have a better and more equitable society. So getting back to where do we use energy in buildings, and I do like to think about this, and it's one of the things that if you're starting to think about buildings, where are the emissions? What is it, where does that relate, or how does it come in? So that commercial buildings and residential buildings are different. So, and we could take an industrial building as well. And a lot of times industrial buildings has to do with the process. But in a commercial building, there's three main categories. And most commercial buildings are offices, but there's lots of other types of commercial buildings. But in a typical commercial building, which would be an office, or we could say non-residential building, the heating, cooling, and ventilation system is usually the biggest use. And that's if we look at national averages. In the Bay Area and at Stanford, Palo Alto, we have a mild climate, so it's less as a proportion. But we can say it's somewhere between a third and a half of energy consumption goes to heating, cooling, and ventilation in buildings. So I'm going to talk a little bit about that. The other area is office equipment and other things that we plug in, so we call those plug loads. And then the third important category is lighting. Lighting, it's everywhere in buildings. So lighting does actually consume a good amount of energy, and it depends on what kind of lighting and things. I'll talk a little bit about lighting. And then there's miscellaneous and other, like elevators and such. There's a variety of things they're in the other category. In residential buildings, it's a little bit more complex because we have things like clothes dryers. There's a lot more domestic hot water consumption in a residential building. We have refrigerators. So there's a lot more things going on in residential buildings, but you can break it down into the heating, cooling, ventilating, lighting, appliances, and water heating. Those are the main categories. So if we start to break it down for each one of those categories, how much energy is being used, what can we do to improve the efficiency of that, and then ultimately what can we do to decarbonize that? So that's, when you start breaking it down into these pieces, it becomes a little bit easier and makes more sense. So again, as I was saying, there's the operational side of greenhouse gas emissions, mostly CO2, and then there's the embodied carbon side, so the two elements. And you can see the pie chart over on the right. If we can get the operational side to be decarbonized, and that's actually pretty easy, and I'm going to show you that, then we've got this little bit more difficult part of the pie. It's smaller, but the embodied carbon. And if you think about it, and if you are at all involved with buildings, you'll know that probably the biggest thing in buildings as far as embodied carbon is cement. Making of cement. Not only does it take a lot of energy, and usually that's like burning natural gas to create the reaction. When the reaction happens, it releases CO2 in and of itself. So 6% plus or minus of global greenhouse gas emissions are related to making cement that goes into concrete. So if we expand out this thought of building decarbonization and start thinking about embodied carbon, what can we do to make a low or zero embodied carbon building? How do we do that? So there's two basic steps the way we do it right now, but it's evolving quickly. First, we select low carbon building materials. So I have a picture of a building with a lot of wood. Wood can now be used as a structural material. I mean, it's been used as structural material for a long time, but we've moved towards using steel and concrete more, and now there's a interest in, can we start using more wood again? Wood has low carbon emissions in harvesting it and preparing it and transporting it to a building, but it also sequesters carbon. It pulls carbon out of the atmosphere, and it's in the wood, as long as that building doesn't burn down, right? So low embodied carbon building materials. Wood is one. There's many, and then with the remaining carbon that is emitted in getting those building materials to the site, you can do things like carbon offsets. And carbon offsets, there's a lot of debate about how valid are carbon offsets, but there are higher quality carbon offsets and there's lower quality ones. So when we're working with clients who want to do offsets, we steer them in direction of higher quality offsets. So a lot of times what we're doing is this comparison for a project. What does concrete look like, steel and wood? And this is the embodied carbon for a building, a 175,000 square foot office building that we were working on. And so we were comparing, and you can see that the concrete structure is not quite, but it's in the neighborhood of twice of the wood. Okay, and so steel is a little bit better, but wood is much better. So there's a lot of discussion. Now, the concrete industry is like, well, wait a minute, this is like bad news for us. So concrete industry and cement, they're starting to think about how can we create different cement mixtures that have the strength that we need, but have lower embodied carbon. And there's this one company that's out there called Carbon Cure, where they inject CO2 into the concrete mix, and it reacts and can create this nano-sized mineral calcium carbonate, which gets embedded into the concrete. So it's an interesting thought. There's a lot of research on this topic right now, not just this particular solution, but lower carbon cements. And there's a lot of that research is happening at Stanford. And there's several startups that are there now that are manufacturing low carbon cement at small scale, and they're hoping to figure out how do we scale it up and make it affordable. So stay tuned, lots of changes are going to happen there. And there's even concrete additives that we can use that are either waste product, usually a waste product or recycled product that can be added to cement that provides strength, but it's a product that we otherwise wouldn't be using, and it displaces some of the cement. So that's something that is actually being done now, and it's been around for quite a number of years. So anyway, there's lots of lots of things to talk about there, but I want to get back to buildings and energy, and the operational side of decarbonization has a lot to do with the energy. The idea is very simple. So first we make buildings more energy efficient, and there's a lot that can be done to make buildings more energy efficient. And then we make that building an all-electric building. So we have an all-electric efficient building, and then we connect that all-electric efficient building to renewably generated energy, or renewable energy, electricity, right? And so the final step is that renewable electricity powering our efficient all-electric building. And that's how we're going to do it, and that's how we are doing it. Many buildings are being built with this framework in mind and are now plus or minus decarbonized, fully decarbonized on the operational side. So let's talk about the efficient building first. How do we get energy efficiency? And just thinking about, lighting, heating, cooling, the different things that I mentioned. Lighting is one of the things that there's been a full transformation in how we provide lighting in buildings. And we started, and many of you probably are familiar with incandescent lights. Then we use fluorescent lights, and there's lots of fluorescent lights in this classroom. And then now we're using LED lighting of all different shapes and sizes. And fluorescent lighting is pretty good. The 60 watt could go down to maybe somewhere in the 15 watt neighborhood, but the LED lighting, a 60 watt bulb, we can actually get LED lighting that's 8 watts now, that's equivalent to a 60 watt bulb. So significantly less energy, but it also, LED lighting lasts 10 times longer than incandescent light bulbs, right? So now we're putting LED lighting in buildings, automobiles, computers, all sorts of different things, and those light sources are going to last significantly longer than what we're used to. So I remember in my house 20 years ago, I'd be changing light bulbs all the time. Now I put an LED light bulb in the lamp or wherever, and that's it. I don't have to think about changing it for at least 10 years, maybe longer, right? So this is the thing. I have an older Prius. It has incandescent light bulb in it, and if it for somehow gets left on, the battery drains really quickly. But also, I have to change those light bulbs every couple of years. And then I recently I was lucky enough to be able to buy a Tesla, and all the new cars that are being sold now have LED lights in the headlights, and they're not set up to be able to change because they're going to last as long as the car lasts. They can be changed ultimately, but it will be at least 20 years, right? So the thing in buildings that's interesting is that we're starting to get back to, actually natural light, daylight, it feels more comfortable. That's what we naturally enjoy. If I asked you what's your preferred lighting, very few people would say, oh, a bright fluorescent light in a classroom. They'd say, like, I'd like to be under a tree and daylight. And so how can we get daylight into buildings? And so there's a lot of work being done on that. We're starting to design buildings that take advantage of daylight so that the electric lights during the day can dim down or even turn off. And it's interesting, the folks at Walmart, Bass Pro, and some of these other large retailers have been looking at this as well, because it saves them money. It's not that, it's not that hard to do. But Walmart took it one step further, where they created two halves of a store. One had the skylights and natural light, and the other didn't. And they took product and they measured its sales in both sides. They moved it from one side to the other, and they were finding that the products that were in the daylight side of the building were selling better than the side of the building that didn't have the daylight. And so now all new Walmart stores have daylight, and they've done it in a really affordable way. There's similar studies in schools. There's been a lot of work on looking at elementary schools, and kids in classrooms that have daylight perform better than kids in classrooms that don't. And I actually remember they were building classrooms in the 70s in California that had no windows, because there was a thought that, well, maybe like windows distract children from learning. But it turns out that was super wrong. And so like all the new generation of schools that are being built have windows, views, daylight, and you'll see around Stanford a lot of the new buildings have great daylight. I will note that GSB, right? Unlike this lecture room with no windows, GSB, almost every lecture room has at least one wall with windows and natural light, right? So something there. Moving on to plug loads, there's lots of good news about how plug loads, the energy consumption of plug loads, how it's gone. When I was working in the early days, a while back, you'd have a desktop monitor. It was one of those deep ones, a CRT, and a desktop computer, and that together would be 150 watts or more. That's set up. Sometimes, if you had a bigger monitor, it could be like 200 or 300 watts. Then we moved, and we've started to move, and you look at where we are now, a laptop with a monitor or just a laptop alone. And the new generation of laptops that you guys are using are very low energy because the manufacturers want the battery to last longer. Battery life has driven the low power consumption computer chips to become a thing, and not only in your laptops, but also in your cell phones. Right? So computer chips now are significantly more powerful than the ones that we had 10 or 20 years ago. And when I say significant, I don't mean 2 times more. I'm talking about 1,000 times or 10,000 times more powerful. But they're using a lot less energy than what they used before. So if you look at that watts per compute ability, that ratio has just gotten incredibly good. On the other side of that, we use a lot more computing. We do a lot more with computers than what we used to do. So the whole cloud and data centers, that has actually become a big energy use data centers that we need to take into account. But in the buildings, the numbers have gotten really quite good. In heating, ventilating, air conditioning, it's a similar thing. We did start out with buildings that were naturally ventilated 100 years ago. There was no air conditioning system. You just had to open the window. Very low energy, but didn't quite work in a lot of climates, right? So we started developing much more complex heating and cooling systems in buildings. The state of the art in the 1950s was this thing called a constant volume system, where you're always running the fan at full speed and you're running the cooling at full speed, and then you use heat to modulate the amount of the temperature in the room, even though the air being delivered is cold. Now we use heat to heat it back up, and it's always going at full speed, constant volume. It was energy hog galore. I mean, really, really bad. And now we're using variable air volume systems that cut the energy down in commercial buildings basically in half. And there's a new generation of heating and cooling systems like chilled beams and radiant panels and things like that, and even low energy versions of variable air volume systems that are significantly better. And if you're looking for a good example of that, the Y2E2 building at Stanford uses chilled beams, and that was built about 10 years ago and is a very lower energy than our variable air volume system. Again, just trying to give you a snapshot of what's possible. When we do a standard pumping and piping system, it usually works out to be around, for a heating and cooling system, about 15 watts are used for every gallon per minute of fluid that we're pushing around, heating and cooling water, right? When I work really hard and I do my low friction design, which I love to do, and my mentor was one of the world's best people on that, we use 45s and smooth pipes, and we design things in a very smooth way. I can get to 7 watts per GPM. But I feel like I'm still a failure because, and you can look this up, the human heart operates at about 1.5 watts per GPM. And in your body are 60,000 miles of blood vessels, so it's quite a complex array and pumping system. And if humans were to try to recreate that, we'd end up with something where your heart would need to be 10 times bigger than what it actually is. So just imagine that. You'd have to eat a lot more food. And spend more time of your day eating, right? So that'd be sort of annoying. So there's lots of what I like to call energy efficiency blockbusters that are now common practice. And I remember, like that upper right, that's the variable air volume box. I remember when I was your guys' age, just starting in the building industry, I made a call to an older seasoned engineer, and he said, "Oh, that energy saving thing, it's not going to work. It's too expensive. It's complex. Don't do that thing. Don't do that." I was like, "Oh, okay, I guess you're right." And fast forward to where we are today, and it's now everybody's doing it, right? So on the bottom right is variable speed drives, and we use those variable speed drives now to control the speed of a fan or pump, so it can go up and down instead of that constant volume, constant flow. We're now varying speeds of pumps and fans, and this is also used in industrial processes and such. So, and then low emissivity windows, LED lighting, all that stuff has really changed how we do buildings. There's a standard for building energy efficiency that many states use and many building designers use as a guidepost for how efficient is your building, or just what's the minimum that we need to do to make it an efficient building. And it's interesting, that standard, which was first written in the 1970s during the oil crisis, people were starting to say we need to think about energy. If you compare a building that was designed to the standard around 1980 to where we are today, and meeting the standard is not very hard. It's in the neighborhood of a 50% lower energy consumption. So we're designing buildings today as a common practice that are 50% lower energy than where we were in the 70s or early 80s. And this standard, for me, pretty much all the buildings I design are using 50% of this standard. So there's another 50% that's easily harvestable. And what I try to do is be out in front so that the people who write the standard know that it's not that hard to do even better, right? So that's been put together. And I did a thing for Duke Energy a while ago, and this was in North Carolina, Duke, where we discussed with a group of people what were the state of the shelf, the things that were off the shelf that we could do to make buildings more energy efficient. So we said, look, the baseline, which would be meet that 90.1 standard, if we apply a better building envelope, better glass, better insulation, not overly complex, and then better lighting with daylight, right? Where the light can dim down automatically. And then we do some plug load improvements, or some things that we could do to get computer energy use down. And then our low friction system, which I was showing you, and then heat pumps. We put that all together and we can get 44% savings, like really easily. I was just saying, state of the shelf, easy stuff. And a lot of folks on the phone were like, wow, it was a video presentation I was doing. But there were several, they were like, yeah, I've done that, right? So making buildings more efficient is not necessarily that hard. We leverage a lot of things that are currently available. Like the thing that I love the most is the efficient building envelope, more insulation. It's passive, there's no moving parts. It's like my solar clothes dryer. So I love the passive strategies. And then we put solar on 40% of the roof and then 80% of the roof. And when we got to 80% of the roof with solar, and this is a 3-story building, then the solar was making enough, on an annual basis, enough electricity for the building. So the building was making all of its own energy. And then we also like to use batteries in buildings now for obvious reasons. So there's a whole new generation of blockbusters that are coming out. Heat pumps are really one of the biggest things. I'm going to talk about that. Integrative design, where we work together as a team to come up with better solutions. That is the architect and the engineer and the builder. If we work in a more integrated process, so if I say to the architect, if you put more insulation in the wall, then my heating system can be smaller. It's very simple stuff. But so much of design of buildings is disintegrated, where architect does their thing, engineer does their, everybody sort of works in separate silos and you don't come up with good results. I think AI is going to be really important for energy optimization in buildings. Buildings generally, especially commercial buildings, don't work very well. They're not tuned up because there's so many data points and there's lots going on. AI is going to help to fix that, and I've already seen a few companies in that area. Induction cooking, which I'm going to show you a little bit about that. And then solar and batteries, of course, is transforming buildings. And that solar batteries is either at the building or at utility scale. So I'm sure you guys are talking about that, right? So there is a professor, Jim Sweeney at Stanford, now emeritus, who wrote with his grad students this book called Energy Efficiency, Building a Clean Economy or Secure Economy. So Jim is interesting because, and Diana knows him much better than I do, but for a long time he was a real skeptic on energy efficiency because he's an economist, somewhat conservative economist who's worked in the Reagan administration. He says, this energy efficiency thing, it's not really a thing. People will just buy it if it makes financial sense and da-da-da, But there were a lot of people pushing him to think about it differently. So he said, look, I'll do a study. I'm going to get my grad students together. We'll do a study. And what they did is they picked apart the U.S. economy and they said, what was the energy intensity or efficiency of airplane travel? So how many gallons of jet fuel per passenger mile over a 30 or 40-year period? And then they looked at industrial, and they looked at cars, and they looked at buildings, and they just picked apart all the different elements of the economy, and then reintegrated that into a macro level perspective. And what they found was that the top part of this, the top wedge in this graph, is the improvements from energy efficiency. So if we had not done, if airplane travel and factories and buildings and lighting, all these things had not gotten more efficient, our energy demand in the US would have been at the top line there. But the first wedge was the reduction that happened from improved energy efficiency. So that was more, and this was through 2015. So we need to update it and everything, but through 2015, that was more, significantly more, several times more than all of the new nuclear or renewable energy that was added to the US grid, right? So this is super significant finding. The energy efficiency is a resource. And so a lot of energy planners and policymakers have been thinking about energy efficiency as a resource and part of the mix of how we meet energy demands or service demands. We don't really have a demand for energy. We have a demand for light or heat and cool. right? So we just want to deliver those same things, but by using less energy. So the next step is this building electrification. And how are we going to electrify buildings? So if you think about it, buildings already use a lot of electricity. Lighting is electricity, right? We don't use gas lamps anymore, thank goodness. But we still do burn fossil fuels at buildings. And we do, most of the burning of fossil fuels at buildings in the US is natural gas used for heating different things. So it could be heating a room, or heating water, domestic hot water for showers, or a dryer, or cooking, right? So in the residential sector, it's still about half of the energy is US. Half of the energy is used for these heating needs. And then in commercial buildings, it's less, like 34% nationally, right? So there's still a big chunk that's natural gas. Meanwhile, the electric grid is getting lower and lower carbon every year. So 160 cities, 8 states, and this is a year or two old, I think there's a little bit more, have already made commitments to be 100% carbon free on their electricity. And so in California, our plan is by 2045, all of our electricity will be carbon-free electricity. That's actually a state law. All of the electric utilities have to follow that, and they're actually well ahead of schedule. And each time there's been sort of a improvement or a ramping up of the requirements, utilities have been able to beat it, a couple years ahead of schedule. So. The electric grid is getting cleaner, and burning natural gas still emits the same amount of CO2, and there's not a lot we can do to change that. So the idea is move over to electricity. And so the different gas uses that we have, how do we electrify them? So the space heating, gas boilers, burning gas to make space heating, one form or another, we can use heat pumps to make heating, and I'll show you that. Domestic hot water, we can also use heat pumps. This is an efficient electric way of making heat. And then gas cooking, we can use induction cooking. So how does a heat pump work? Well, if we compare it to a boiler, when we're burning natural gas, you put 100 units of gas in, and we'll get somewhere around 85 units of heat out, 85% efficient, right? But with a heat pump, it's really interesting. It uses the refrigeration cycle, which is in air conditioning systems, refrigerators, your car air conditioner. We use the refrigeration cycle to pull heat out of air, out of the outside air. So even on a cold day, we can pull heat out of the air. And sometimes you pull it out of the ground with a ground-coupled heat pump. So we use the electricity to run the compressor. The electricity isn't actually turned into direct heat. It's used to run the compressor that then puts heat into whatever form, air or water, that we're trying to create to heat a building. So we can put 100 units in and we get 300 units of heat out, right? Remember over here on the gas, we put 100 units in, we get 85 out. So this is significantly better. It's, in a sense, 3 times better or more in most heat pumps, improvement in efficiency. So that is a very big deal. And this is what heat pumps look like in a residential setting. And the ones on the left look a lot like an air conditioner, and that's because they are. They're a heat pump that can make heat in the winter, and then it reverses in the summer, it can make cooling. So that's one of the nice things about heat pumps is it can do both. So you can, on the residential side, you can buy one piece of equipment to do both. If you're in that climate that needs both, right? And there's a new generation of these smaller units that are more efficient than the ones on the left. And they're widely used throughout the world. And it's heat pumps in residential are a big part of Europe's plan to quickly and rapidly get off natural gas because of the Ukraine war, natural gas supplies were rapidly diminished, and so part of the solution was like, let's quickly ramp up the use of heat pumps. There's a huge growth in the heat pump sector globally. That is, the manufacturers are really doing quite well. But there's commercial versions of heat pumps as well, and this is where I work, and these are a couple of buildings that I've done where we have big racks of heat pumps on the roof, and there's different types of systems, and they'll make heating and cooling or just hot water. The one on the right is for making hot water. The one on the left is what we call variable refrigerant flow. It makes heating and cooling. And if one zone of the building needs cooling and another needs heating, it actually, the heating gets transferred from the hot zone to the cold zone with very little compressor activity there. So there's some real interesting things that are happening with this new generation of heat pumps. And then there's very large scale heat pump systems. This is the Stanford Central Energy Plant. And the Stanford had a large cogeneration energy system that was installed, I think, in the early 80s. And it burned natural gas to make steam, electricity, and then they used the steam in this special kind of cooling system so they could make chilled water distribute around the campus. It turned out that cogen system was the single largest CO2 emitter for Stanford as in its CO2 footprint, like by far. It totally dominated. And it was coming up on the need of a major renovation and upgrade. It was going to cost millions of dollars. And luckily, Stanford decided to not proceed with that very expensive upgrade to a system that would lock Stanford into very high CO2 emissions for several more decades. And they scrapped that system and they built this new central energy facility. And what it is there's these big, what are oftentimes called chillers, but cooling machines, refrigeration machines that are set up to do heating or cooling or both. And then the tanks that you see there are big thermal energy storage tanks. So when in the afternoon on a warm day, there's lots of cooling at Stanford. So they're sending cold water from the central plant out, but what's the waste product of making cooling? It's heat. Because when you cool the water, you're pulling heat out of the water. And so it's waste heat. So what they do is they store that heat in the tank, in one of those tanks, and then the next morning when you need morning warm up, there's lots of days where there's cooling in the afternoon and heating in the morning. The tank will be full of hot water and they'll send that through to the campus, and the campus will start using the hot water that was made the day before as a waste product. So it's very, very energy efficient, but it's also all electric, right? So this is that heat pump idea on a large scale. When we start talking about cooking, when we burn natural gas in a kitchen, inside, it not only releases CO2, but it releases nitrous oxide, carbon monoxide, formaldehyde. And there's a recent study by Stanford, benzene is another thing. And all of these things are in concentrations that are unhealthy. And this is one of the things that adds to people's, getting things like asthma. And the rate of asthma in the US right now is very high as compared to where it was before. And so we have tighter buildings, good thing for energy, but not so good for ventilation. And so gas stoves not only are gas and emit CO2, but they are not healthy for people. So there's a big push now to rethink how we're doing cooking in homes. And so there's a whole generation of electric induction cooking, and this is the commercial version. And induction cooking is different than using electricity to create a hot element that turns red. Many of you might have seen that kind of electric cooking. It's unsafe and it's not very good. It's not very fast. But induction cooking is where you create a magnetic field with a coil underneath the glass, and that magnetic field, when the pot is one that responds to magnetic field, so not copper, not aluminum, it needs to be steel, stainless steel, cast iron, those kind of pots. then it heats the pot itself and nothing else. And so the pot actually can heat up quite fast. I have an induction stove in my home, and it boils water faster than the gas stove I had before that, and it was a nice gas stove. And it also is very good at being precise. So I can turn it down to halfway or a quarter way, and it quickly responds to that. So it's actually quite nice. And now there's a growing number of high-end restaurants that are starting to discover the induction cooking. It's good for cooking, but it's also safer for people who work at the stove because the air quality also burns, and because you're not heating up the surface or the surfaces around a gas stove, it's easier to clean up. So I think we're going to see this really take hold. I work with a lot of commercial tech clients in the Bay Area and also abroad, and they're all their new commercial kitchens, like restaurants, they're putting in as 100% electric. All right, so building renewable energy, the last little piece is how do we take our efficient electric building and get renewable energy? The cost of solar panels has gone down so dramatically. I can't tell you. I remember when I was your age saying, oh my God, if we could just get below $10 a watt, it'd be so good. It was like 15 or 20. And we're now to where we are now, we're below $1 a watt. We're like 25 to 50 cents a watt for the module, the solar module itself. It's incredible how far it's come down. And so consequently, the demand for solar photovoltaic systems is skyrocketed globally. And worldwide last year, 70 to 80% of all new electricity additions to the grid globally were renewable energy, so wind and solar. And most of that was solar, and wind and solar are beating the other forms of electricity generation because they're cheaper and they're faster to deploy. So we're seeing that happening, but solar on buildings is actually a fairly practical thing. In most of the places where I work, putting solar on a building will generate electricity cheaper than buying electricity from the grid. And I have lots of friends who I've convinced to do solar on commercial buildings. They're not like super environmental. They're not green or anything like that. But when I show them the numbers, I say, in California, we can generate solar electricity at 10 cents a watt. Now, it's a little bit more expensive, solar in California, because our labor rates are higher. But it's around 10 to 12 cents a kilowatt hour. Whereas buying it from the grid is between 15 and 17 cents a kilowatt hour. So when I show the numbers, I have a friend who owns a large construction company, and I showed him the numbers, and he's like, okay, we're going to do that. And last time I saw him, he gave me a big hug. He was like, Peter, you're so great. I love you, man. So it's like, okay. All right. And then there's this whole idea of net metering and the evolution of net metering. I'm not going to get into that, but that makes solar practical. The other thing that's happening is the cost of batteries is coming down. And we're not at the bottom of the curve on that at all. But battery storage is going to make not only storing solar energy that we generate during the day and make it available to us at night, right? It's not only going to be able to do that, but we're in this heavily dominated by renewable grid that's going to eventually occur. We're going to have the duck curve and some of these other things where electricity is going to be really valuable at night, and being able to store from the day into the night, either at the building or at the utility scale, is going to be really important. So we're actually finding batteries are cost-effective, financially cost-effective now, where utilities have time of day rates and seasonal rates, so that where there's a big difference between daytime and nighttime. And so what some people, some buildings are getting batteries with no solar. They charge up the battery in the middle of the day when electricity is its cheapest, and they discharge the battery in the early evening when electricity is most expensive. So we call that energy arbitrage. It's not really proper arbitrage, but that's what's happening. Is that building owners are now buying that as a thing. So lots is happening. And there's the power wall, the thing on the right. We've seen the thing that people put in their homes, but Tesla and other companies are now making big battery banks that are designed to go with buildings. So we can get solar and batteries at the building, but what if you have a large building or the roof area is not big enough for solar? Well, we can do this community choice aggregation or different versions of that, where in many places in the US now, you can select what your generation is and where your generation dollars go. And we have this in California, but it's lots of other states where I'm doing projects that's available. And the incremental cost of buying the renewable generated electricity is typically in the less than 10% increased cost. So, very modest cost and, getting lower every day. So that's really good news. All right, so I wanted a couple barriers I want to talk to you guys about. The manager barrier. Why? So if all this stuff makes so much sense, why isn't everybody doing it right now? Well, there's lots of reasons, but I wanted to show you a couple. And we were talking about this earlier today. I'm working with a company. They have a big facility in Miami. And we said to the CEO of the company, it's a multinational, was like, our company is going to go carbon neutral by 2035. We got lots of money, go out and do it, And so we're with this national facilities meeting with all the people, and the guy from Miami is like, yeah, we have to redo our roof because it's old. And we're like, well, you're going to put solar on the roof, right? And he's like, no, I'm not going to put solar on the roof because, there's hurricanes in Miami, and the panels could blow off. There could be leaks, and the space underneath is like really critical space. If there's water in there, they'll have to shut it down, and everybody will get upset. And this guy, he didn't say it, but he was probably thinking I could get fired. Solar panels in hurricane areas is a thing. They have to be more heavily secured to the building, and there's a whole slew of methods to do that. So this problem of them blowing off the roof is very easy to mitigate. But he didn't want to hear about it. And that's because for him, there was all risk and no reward. He's just thinking about all these bad things that could happen. But what's in it for him? Why would he take all this risk? If it's successful, he maybe gets a little pat on the back or something. It's like not interesting to him. So I'm talking to that company, and they're actually, I think they're going to do it, about creating a series of incentives for the managers who are managing these facilities to get them to see it risk and reward. So KPIs is this key performance indicator that you're evaluated at the end of the year. How much did you achieve? And people do respond to that. And there's also recognition. You can get an award or something where you're publicly recognized within the company. But I think financial is probably the most important one. This particular project was going to cost well over $2 million. And if they just said, well, we'll allocate 1% or 2% of the project to a bonus for the guy who manages this thing, who makes it happen, and that would be $25,000 to $50,000 out of a $2 to $3 million budget, it's very doable. And so suddenly that manager is looking at a $50,000 bonus, and instead of seeing risk, they're going to see a lot of reward, and they'll make it happen. Right? So it's very interesting. We've had over time, the barrier has been the people at the C level, the CEO and such, are like, no, we're not going to do any of that stuff. That's changed. Now the C level in many companies, like, we're going to do all this stuff, and now we're getting to the next level, which is the managers who manage buildings and projects and such. So there's another one that I was literally just today on a phone call with a large company, and they're like, well, we have all these goals. We're going to be carbon neutral, and it's, again, a multinational company, and their stated goals are very aggressive. And I've seen their buildings. They're very energy wasteful. So I'm not going to tell you their name, but I just, can't believe it, right? How much energy they're wasting. I'm like, guys, you got to get on it, And I said, they said, well, what's the payback? How fast will it pay for itself? And I said, well, it's payback's not the right way to look at it. It's talk about return on investment or net present value. This is what MBAs think about. People who manage money in these large companies. And it said, well, the return on investment is well above 20%. They can borrow money in the neighborhood of 5 to 10%. And we can give them a guaranteed, and it's very low risk, 20%, 30% return on investment. So that, like, financially, it's a no-brainer. But the guy that I was talking to said, no, we can't do that. Because that translates into this thing, payback. Everybody, it's a simplistic way of looking at an investment, is how long does something take to pay back? So he said, well, 20% return on investment is a 5-year payback, meaning it will take 5 years. If I spend $1 million, I'll save $200,000 every year. 5-year payback. And he said, we don't do 5-year payback. We do 3-year and sometimes only 1 year. Meaning if I spend $1 million, I have to save $1 million in the same year. That's over 100% return on investment. It's ridiculous. I mean, that's really good. But what it does is most of the bigger energy savings, it compromises going after them. And so, you know, when I'm talking to my clients, I say, no, don't get into this payback trap, you know. And I on the phone, I was trying to, you know, coax this guy down, you know, and say, come, we got to look at it a little bit more rationally here, and we got to talk to the MBAs in the company. And that particular company has a lot of them, so. Anyway, just a couple of case studies. We're doing the AIA, American Institute of Architects headquarters building in Washington, D.C., built in the 1970s. It's right near the White House, a really significant building. And we're making it efficient. We're going to replace the windows, we're putting in new lighting, and we're doing a variety of other things to make it more efficient. Then we're electrifying. We're taking out these natural gas boilers, putting in heat pumps up on the roof. And then they have a little bit of solar on the roof, but it's only 10% because it's a 7 or 8 story building, and they can only fit a little bit of solar on the roof. So they're buying in Washington, D.C., there's this program through the utility, PEPCO, called DC Power Connect, and you can choose your electricity generation, and they're choosing this one called Clean Choice Energy. So they have 100% renewable generation, wind and solar. Right, so all their generation dollars in their bill goes to Clean Choice Energy, who buys renewable electricity. So they're getting efficient building, electrified building, and 100% renewable electricity. So they're decarbonizing the operation. Now, in the embodied carbon, they're saving 80% of the embodied carbon by reusing the building and not building a new one. That's the biggest win, is to reuse the building. In the US, we have lots of buildings. We don't need to build that many more buildings. So they're doing that, but they are putting in new glazing, new furniture, that all has embodied carbon. What they're doing to offset the embodied carbon is they bought, and this is already happening, they bought solar panels and the inverters, and they donated them to Habitat for Humanity, who's then going to install them with their labor. But part of the deal is we donate these solar panels to you. We get 100% of the credit for the carbon reduction. And so the Habitat guy said, fine, that's great, because all we care about is low energy bills for the people that we work with. And so this is all happening in DC and Northern Virginia. So it's helping the community have lower bills, and and create affordable housing. So it's like helping the community, but it's also getting them to fully decarbonize on the embodied carbon side. So it's a very creative, interesting thing. So this building, which is under construction now, when it's done, will be a fully decarbonized, both embodied and operational renovation of a large building. It's a super significant, one of the most important building renovations that's going to happen in the US over the next couple of years. So keep an eye out for that. And then I just want to end with this emphasis. I've been working with a company in India for well over 15 years now, and they have 30 million square feet of office space. It's a very large company. It's a tech company, IT company in India, 250,000 employees. I think the number is now closer to 300. But lots of employees and lots of buildings. And we started working together, designing low energy buildings, and it worked, and it worked. And they just they created a whole department of 15 or 20 people chasing energy efficiency. And over that period, they've reduced their per capita energy consumption by 55%, which is amazing. I don't think there's any other large company globally that's achieved anywhere near as significant energy savings as this. So it's not just something that makes sense in the US, this also makes sense in a wide variety of countries. So we're doing that. And then just so you know, this is the Building Decarbonization Learning Accelerator that I founded with a couple other people at Stanford. And what we're doing is we're making teaching material available to professors at other universities around decarbonization because it's such a significant topic that needs to be rolled into all architecture, engineering, and construction management programs. So we have, I was telling Diana earlier, we have almost 1,000 people who are now using the material. Thank you very much.